In the previous lecture, we defined sequences, and we talked about what it meant to say that a sequence converged to a real number or diverged to infinity. In this lecture, we're going to go through a few results about sequences. The first one is called the squeeze theorem. This is probably familiar to you from calculus. You may be imagining the squeeze theorem about any functions. Here we're talking about the squeeze theorem applied to two sequences. So suppose we have two sequences an and bn, and they are both converging to the same limit L. Introduce a third sequence cn which sits between them so that an is less than or equal to cn is less than or equal to bn for all of the indices little n. If c is sitting between them, then essentially c is going to be squeezed to the same place. So if an and bn are both trending to L, so is c. This is not too hard to picture. On the top we have a sequence bn which is converging to L, so as n goes to infinity, the terms in our sequence are trending to the number L. Likewise, underneath that we have another sequence an which we also know to be converging to the same limit L. Now suppose sitting between these two sequences is a third sequence, so here's C1, C2, C3. This sequence appears to be trending to the same limit L, so that's what we're going to prove. To prove the squeeze theorem, we want to show that Cn satisfies the definition of convergence. So given some arbitrary positive number epsilon, there exists a threshold capital N so that for all indices beyond the threshold, the distance between the term Cn and our limit L is less than or equal to epsilon. So that's the goal, is we're just going to show that Cn satisfies the definition. As is often the case with these proofs, the first step is to declare epsilon to be an arbitrary positive number. Next, we're going to use the fact that we know that an and bn are two sequences which both converge to L. So what we're going to do is ultimately choose one threshold capital N which simultaneously works for both of them. It's like if N1 was the threshold for an and N2 was the threshold for bn, we're going to choose the maximum of those thresholds. So choose the threshold capital N large enough so that for all indices beyond the threshold, the distance between the an terms in the limit is less than or equal to epsilon, and ditto for the bn terms. Now what we're going to do is use the fact that the cn terms sit between them. So let's establish kind of a large inequality. Let me build this up step by step. So first, we're given that an is less than or equal to cn is less than or equal to bn. Now go through and subtract L off of each of those expressions. If we unfold the two inequalities which we know to be true because an and bn are both convergent sequences. So if I take those two inequalities and unfold them to remove the absolute values, we can say that on the left, an minus L is greater than or equal to negative epsilon, and on the right, bn minus L is less than or equal to epsilon. Now we have 5 expressions. We actually only need 3 of them. So let me underline what's important here. With these 3 terms, I can fold this expression back into the type of inequality we want to show is satisfied in order to show that Cn converges. So let me just grab these 3 terms and put them back together using absolute values. We can say that for all indices beyond the threshold, the distance between Cn and the limit L is less than or equal to epsilon. At this point, we've showed that Cn satisfies the definition of convergence with limit L. Now let's look at the algebraic limit theorem, which gives us a way to combine convergent sequences to form new convergent sequences. So suppose that an and bn are two convergent sequences. The limit of an is a, the limit of bn is b, and let kappa be any real number. Then an plus bn is a convergent sequence, and the limit of the sum is the sum of the limits. So the limit of an plus bn is a plus b. If you take a sequence and multiply it by any number, call it kappa, that results in a convergent sequence, and the limit of kappa times an is just kappa times a, so you can essentially pull that scalar multiple out front. Likewise, the product of two convergent sequences is also a convergent sequence, and the limit of the product is the product of limits. And then if we're not dividing by 0 so that everything is defined, the limit of the quotient is the quotient of the limits. We're going to prove the first 2, and then for the third one I'm going to give just kind of a sketch of the proof, and you can prove the fourth one on your own. So for the first one, I want to show that an plus bn as a sequence satisfies the definition of convergence. Our first step is the usual. We're going to let epsilon be greater than 0. Next, I know that AN and BN both converge, so just like we did with the squeeze theorem a minute ago, let me choose a threshold which simultaneously works for both of them. I'm going to go ahead and kind of naively write down what it's going to mean to say that it works for both of them. So let's choose capital N large enough so that for all indices beyond capital N, the distance between AN and the limit A is less than or equal to epsilon, and the distance between Bn and B is also less than or equal to epsilon. My epsilons here look a little bit funny because we're actually going to modify those a little later, but I want to show you what kind of expressions you can encounter if you just kind of start trying to prove this. So I know exactly what I want those expressions to be, but let's say for the moment I didn't, so I could just kind of leave those as epsilon and make a little adjustment later. All right, so now let's consider indices beyond the threshold. I want to show that the distance between AN plus BN and A plus B can be made less than or equal to epsilon. So let's see what that looks like. Here's the distance between our new sequence and our desired limit. Of course, first thing to do is rearrange those terms. So let me group the A's together and the B's together. Next, we're going to apply the triangle inequality. Now notice what we have here. We've got AN minus A, BN minus B, and we're saying that our indices are beyond the threshold. Well, we've already said that if you're beyond the threshold, AN minus A is less than or equal to epsilon, and so is BN minus B. So now we have that this is less than or equal to epsilon plus epsilon, which is 2 epsilon, and honestly, that's enough, but because this is a first semester analysis course, let's fix this proof so that we really do end up with exactly epsilon at the end. Keep in mind that AN and BN both converge, so given some measure of closeness I want to satisfy, I can choose a threshold that forces the terms in the sequence to be sufficiently close to their limits. In this case, I don't want them to be within epsilon of the limit. I actually want to choose capital N large enough so that each of those terms is within epsilon over 2 of their limit. And you can do that because AN and BN converge. So you can pick a threshold that makes them as close together as you like. Traditionally, we call that epsilon, but it could be epsilon over 2. It could be epsilon divided by 100. So you can scale that bound on the right-hand side in order to make your proof really end up with epsilon. Now we've shown that AN plus BN as a sequence satisfies the definition of convergence, so we can conclude that the limit is A plus B. Let's prove the second part of the algebraic limit theorem, which allows us to pull constant multiples out in front of the limit. This is the kind of proof that it's going to be in 2 cases, and what would typically happen if you were proving this for the first time is you would be playing around with it and kind of discover these 2 cases yourself. So the first case is that kappa is actually 0. If kappa is 0, then the limit of kappa times anything is just the limit of 0. And then the limit of the constant 0 sequence is 0. But since kappa is 0, we can reinterpret that as kappa times A, right? So kappa here is 0, so that's 0 equals kappa times anything. And that's our first case. Go ahead and get that out of the way because we're going to divide by kappa in a minute, and we want to make sure we're not dividing by 0. So for our second case, we're going to do an epsilon proof and show that kappa times AN satisfies the definition of convergence. Again, we have a sequence which we know converges. We know that AN converges to A. So given epsilon greater than 0, I can choose capital N large enough so that the distance between AN and A is as small as I want to force it to be. Again, in this proof, I know how small I want it to be, but I'm going to pretend that I don't and then make an adjustment after the fact. So since AN converges to A, choose the threshold capital N large enough so that for all indices beyond the threshold, the distance between the terms AN and the limit A is less than or equal to, let me write epsilon there, and obviously that's going to get adjusted in a minute. Now let's look at what happens when we consider kappa AN minus kappa A. I want to show that the distance between those 2 terms is suitably small. So for all indices beyond the threshold, what we're going to find is that the distance between kappa AN and kappa A, well, notice kappa here is just a number it can factor out. It could be positive or negative, so it's going to factor out with its own set of absolute values. Now we've got this number out front, AN minus A right here. Well, for all indices beyond the threshold, This expression we've currently set to be less than or equal to epsilon. So now we've got kappa times epsilon. Again, that's not bad, but let's adjust it to make sure we actually land on epsilon at the end. If I go back up to this expression, I could have chosen capital N large enough so that this expression is less than or equal to epsilon divided by the absolute value of kappa. There, kappa is not 0, so we're not doing anything illegal. And what we now end up with is epsilon. So once again, we've shown that the sequence kappa an satisfies the definition of convergence. So we conclude that the limit of kappa an equals kappa times a. Now let's look at the third part of the algebraic limit theorem. This says that the limit of a product is the product of the limits. Notice here that it's assumed that an and bn are both convergent. I can't stress this enough. You cannot use the algebraic limit theorem if an and bn do not converge. You must know that they converge. So you can't say the limit of the product of two divergent sequences is the product of the limit or something like that. Okay, it has to be convergent sequences. This proof follows the same methodology as the previous two proofs. We want to show that the sequence an bn satisfies the definition of convergence with the limit ab. The proof itself is a little bit more involved. We're going to do all the work, but instead of writing up a formal proof, let me just show you what the work is. So let's just do scratch work. Assume I've got epsilon greater than 0. I want to show that the distance between a and bn and ab could be made less than or equal to epsilon. So let's look at that distance. This is harder than what we saw in the proofs of parts 1 and 2 of the algebraic limit theorem. Nothing factors out here. It's not like kappa, which just factored out in front of everything. I can't just rearrange terms like we did in the proof of the first statement. So what we're going to do here is use what I call a fancy zero. We have a and bn minus ab. Between these two terms, I'm going to introduce in something which cancels out, so that's why it's a fancy zero. And the idea is that we're going to step from a and bn to ab using additional terms for which factorization is possible. So what am I going to bring between them? Let's bring between them minus abn plus abn. That cancels. And now notice that from those first two terms, I could factor out a bn, and from the second two terms, I could factor out an a. So let's do that. We're applying the triangle inequality at the same time. Okay, now let's look at this. an minus a, this is a great thing to see because we know that an converges. bn minus b is also a great thing to see because bn converges. Absolute value of a is just a number. Could be 0, could be 100, but it doesn't matter, it's just a number. The only thing here which might seem a little hard to deal with at first is bn. But remember that bn is a convergent sequence, and we have one good result about convergent sequences, which is that they are bounded. So I'm going to take that expression and bound it by the letter capital M. So let M be a bound on that. Let me go down the line. I'm not going to write everything at first. Let me just write two fixed numbers here that I can see. Okay, so bn is bounded by M, and then the absolute value of a is just a number. So those are just two numbers. We think back to some of the proofs we've done, and what we would like to see here would be something like epsilon over 2 plus epsilon over 2, right? We've got two parts here, this part and this part. It would be great if I could show that each of those parts individually was less than or equal to epsilon over 2. Well, here for this first part, we're almost done. We've got this number m. So what if I forced an minus a to be less than epsilon divided by 2 times m just to cancel out the m's? Since an converges to a, I could choose the threshold large enough so that this distance was less than or equal to epsilon divided by 2m. That's just a number. Likewise, bn minus b, you might be tempted to write epsilon divided by 2 times the absolute value of a, from which you could break it up into two cases, a is 0 or not 0, but there's a little bit of a trick. Let's write epsilon divided by 2 absolute value of a plus 1. The nice thing here is that this is not 0. Even if a is 0, it's not 0. This is strictly positive. And then this expression is not exactly epsilon over 2, it's less than epsilon over 2. And that's because if you just look at the parts that have the a, it turns into a divided by absolute value of a plus 1 or absolute value of a divided by absolute value of a plus 1, and you can try a few different versions of a, that number exists, and it's always strictly less than 1. It's between 0 and 1. So this expression, we didn't exactly get epsilon over 2, but we got something even smaller, which is good. So now we can say that this is less than epsilon over 2 plus epsilon over 2, which equals epsilon, and from that point we're good. So the key idea here is that you want to pick your threshold capital N so that an minus a is less than or equal to epsilon divided by 2m. M is the bound on b, that's just a fixed number. And bn minus b is less than or equal to epsilon divided by 2 times whatever a's limit is, again that's a fixed number, plus 1. Lastly, let's look at a group of statements I call the order limit theorem, because it's a theorem about how to order limits if you know that you have convergent sequences. So suppose an converges to a and bn converges to b. If a is a sequence of non-negative terms, then the limit can't be negative. If a is less than or equal to bn, then the limit of an must be less than or equal to the limit of bn, so a is less than or equal to b. And then the third one is just kind of almost like a rephrasing of the first one, but without 0 here. So if there exists some real number which is less than or equal to all of the terms bn, then it must be less than or equal to the limit. So compare that with the first part. Similarly, if it's greater than or equal to all of the terms of a sequence, then it must be greater than or equal to the limit. In other words, you can't jump over c. In the first one, you can't jump over 0. These proofs are all very similar, so we're just going to prove the first one. This is easiest with a proof by contradiction. So a proof by contradiction takes P and not Q and shows that it is absurd. So P here is going to be the hypothesis that all of the terms of our sequence are non-negative. Not Q would be the opposite of the conclusion, so we're going to assume A is strictly less than 0. So that will be our assumption. Let's sketch a picture so that you can see. Let's sketch a picture so you can see how the argument follows. Here's the number line. There I've indicated 0. Imagine that A was strictly less than 0. If it's strictly less than 0, no matter how close it is, there's got to be a measurable distance between 0. So what we're going to do is choose epsilon so that all of the points which are within epsilon of the limit A kind of live to the left of 0. So in particular, if we choose epsilon so that A plus epsilon is over here to the right and A minus epsilon is over here to the left, according to the definition of convergence, we should be able to find infinitely many points from our sequence which live within distance epsilon of the limit, but that puts them to the left of 0. That violates our hypothesis that they're positive, and that's going to be our contradiction. So now let's write that up. As I always say, whenever you're doing an indirect proof, it's good to indicate that so that the reader can follow the argument. So for the sake of contradiction, suppose that an converges to A with A negative. Now I'm actually going to choose a specific value of epsilon. Let me have epsilon be negative A divided by 2. Notice A here is negative, so negative A is a positive number divided by 2 is positive. Since our sequence an converges to A, there must be a threshold large enough so that for all indices beyond the threshold, the distance between an and A is less than or equal to epsilon. In other words, we should be able to say that for all indices beyond the threshold, the terms in our sequence need to live in this kind of region I've drawn around A in the picture. But what does that mean? Well, it implies that an is, and here I'm essentially going to unfold this inequality, but I'm only going to focus on the right half. So I could say negative epsilon is less than or equal to an minus a is less than or equal to epsilon, where I've removed the absolute values, but we're just going to look at the right half. So an minus a is less than or equal to epsilon, or in other words, an is less than or equal to epsilon plus a, but that's just a minus a halves, right? I actually have a value for epsilon here. So that's actually going to be a halves. And that's a negative number. And that's a contradiction because we assume that the terms in our sequence were positive. Since we've established a contradiction, it must be the case that the limit a is greater than or equal to 0.